when in our lessons 2.6 today, solving compound inequalities, we're going to use all the skills we've also learned in this chapter where we're working with simple inequalities. Everything you've solved so far is just called a simple inequality. Simple inequality does not mean just do one step of work. It's that simple. It means there's only one inequality symbol in the statement. A compound inequality has more than one inequality in the statement. So compound inequalities are two inequalities. Basically, they're combined together into one inequality called the compound inequality. And for those of us who did do our homework before today, what words do they use for the two different types of compound inequalities? Nicholas?
And or.
And? Or, yeah. And, or. So it has to meet one, basically what it's setting up is there's like two different conditions. If it's an and one, it's saying, you know what, it has to meet two conditions together. If it doesn't meet both of them, then we can't call it an and inequality. We can't call it the solution to that inequality. So if your parents say to you, you can't go out this weekend with your friends unless you clean your room and you do all the dusting in the rest of the house. So they use the word and in there. What does that mean then?
You have to do both.
You have to do both, or you're not going out. If you only clean your room and say, I don't like to dust, I'm not doing the other part, are you going to get to go out? According to what they said. Don't talk to me about how easy your parents are. If you're really supposed to do both, you have to do both to be able to get to go out. But if they put it like this, clean your room or dust the rest of the house, do you get to go out if you only do one of them? So if you only clean your room, do you get to go out that weekend?
Yes.
Yes, you do, because you only have to do one or the other. When we're solving our compound inequalities, that's how our solutions are going to work. We only have to do one. Sometimes the solution only has to meet one of the situations or the other. Sometimes it has to meet both of them. The and would be when it has to meet both. The or when it has to only satisfy one of them. So compound inequalities are two inequalities graphed on the same number line. We don't make separate number lines, even though there's kind of like two situations going on, two inequalities involved. We graph the solutions on the same number line. So when a compound inequality uses the word and in it, we are looking for where, just like you said, both of them have to be true. Both things have to be satisfied for it to be a member of the solution set. But when we have compound inequalities that use the word or, no, it's either one. It doesn't matter which one it satisfies. So both of them, as long as it satisfies one or the other, makes either part true, we get to call it a solution. So when it's an and, it has to make both inequalities that are part of the compound inequality true. When it's an or, it only has to make one of the two true to be included in the solution set. Okay, when those of you who did do this and solve them, it was example 2, I believe, is where you started solving. So even if you didn't do your SQ3R, or you did, let's look at example 2. What happens when you solve compound inequalities of the and type? Patience?
You take one on the left side of the inequality sign, and then what's in the middle for the first one, and then what's in the middle and what's on the right.
Okay, so we can take the x plus 2 that's in the middle and say it can be, one of the simple inequalities that is a part of this says x plus 2 has to be, reading it backwards, greater than negative 3. So this is one of the simple inequalities, and the other simple inequality is x plus 2, same statement, same expression, but it has to satisfy b is less than 7. And it's and. So two simple inequalities. That's one way to do it. In fact, that's how they did it in part A of example 2. What did they do in part 2 of example, or part B of example 2? What did they do? Did they break it into two simple inequalities?
No.
No, they just left it all as one and solved it in that state, didn't they? So we can leave it together, or we can separate it and make it into two simple inequalities and solve it that way. We're going to do both right now just to see what happens, okay? So if this is the one we're used to solving these. What are we going to do to solve this simple inequality?
Subtract 2.
Subtract 2. Okay, subtract 2 from both sides. Come over here and do the same thing, right? We've got two simple inequalities to solve. Both are going to have the same thing happening. This one's solution is?
Negative 5 is less than x.
Negative 5 is less than x. And?
X is less than 5.
X is less than 5. So this is telling us that x has two situations to satisfy. Whatever you want x to be, it has to satisfy both of those. X has to be greater than negative 5. Give me some examples of some numbers greater than negative 5. Dylan?
Negative 4.
Negative 4.
1.
1.
A million.
What? 13. A million. Okay, there's a whole bunch of numbers greater than negative 5. But wait a minute, it says, and that number you pick also has to be less than 5. So which of those numbers do we now have to throw out that you just said?
A million. Anything above
13 and a million and
yeah, anything above 5.
how about 5? Is 5 included?
No, because it's not equal to. So
No, it's not included, is it?
so the numbers you can use are negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 4.
Okay, how about anything in between them? Like the fractions and decimals and
Yeah.
Yeah, okay. Well, can it include negative 5?
No.
Can it include positive 5?
Nope.
But anything
In between.
in between. Okay, let's graph that. Negative 5. We're not going to worry about the integer neighbors now in these compound inequalities. We're just going to work with the two endpoints that help us show the compound inequality solution. So you said negative 5 is not included. You told me 5 is not included. But you said everything in between is. Okay. So it has to satisfy both of them. You can't just satisfy one or the other. Can it? Okay, well let's go over. This is probably, right here, this is probably not how you would see the inequality solution in an answer bank. They're going to bring that back together and write it as a compound inequality without the word and in it. They do not typically have the word and in a compound inequality that represents that situation. So what you're going to do is you're going to have to bring that back together. So if you solve it this way, now you say, okay, I got to bring this back together. So this x that's kind of like, let's bring this over here and throw it on top of this one. So this would be written how? It would be negative 5 is less than our x. This x is going to come on top of that x.
So, and then is less than 5.
Is less than 5. This is how we would see it in an answer bank. Well, here's the way I like to solve these. Instead of breaking them into two simple inequalities, because I don't want to have to go through the work of bringing it back together like that, I'm going to do this the second way they showed you in your book. And what did they show you in the book for that one? What would you do? Look at example 2, part B. What did they do? Nita?
You just subtracted 3 from every part of the.
Yeah, there's like, how many parts are there? How many parts are there? 3. 1, here's a region right here. Here's a region, and here's a region. They just do it, you just leave it as it is, and you say, oh, just got to do it to all the parts. We can't just say to one side or the other, because this has 2 inequality symbols in it. So it creates 3 regions. So, but we're not going to subtract 3, we're going to do what? Subtract 2. Just like we did over there, but we're going to kind of, this is kind of like almost needing to shortcut it. Do it to each region, and we should get the same thing. Much shorter, isn't it? Yeah. Than breaking it apart into 2 inequalities and then having to bring it back together. Just do it Will it have the same graph as the graph we already put together? Yeah, it's the same. It's still the same inequality. We're just showing that there's two different ways to go about solving these. When it's this type, we can do that. We get to make a choice. So you go ahead and solve the next one then. You decide, how do you want to do it? Do you want to break them apart? Or do you want to solve it by doing it to the regions? Go ahead. Suppose we just keep in mind all the same rules we've done for solving simple inequalities, even when we do leave it together. What's the only thing that's different about solving inequalities from equations? What's the only thing we have to be careful of? If we multiply or divide by a negative, we have to reverse the signs. Okay. In this one, do we multiply or divide by a negative?
No.
No, so we just leave the signs the way they are. Okay, how many of you solved it using the breaking it into simple inequalities method? Okay, and so were your two solutions this? Were they negative 2 is less than or equal to x, and x is less than or equal to 3? Okay. So then when you bring them back together, remember the x's kind of come on top of each other and we still get the same solution, don't we? Okay, how does this look on a graph then? John?
I put negative 2 on the, yep, and then negative,
Here?
yeah, and then negative 3 on the other side.
Is it negative 3?
Or I mean positive 3.
Okay, because that's their order on the number line, right? Okay.
And then I colored in both circles on both dots, and then it's any number in between those two. So it's a squiggly line.
Okay, why is it any number in between? I want to know why. Just because the last one was? I want you to reason out for me, why is it any number in between? Kenzie?
Because x has to be greater than negative 2, and it also has to be less than 3.
Yeah, x has to be greater than, when we read this, it says x has to be greater than negative 2. Those guys go this way, right? Okay, and this one says that x has to be less than or equal to 3, and those go this way, but it has to meet both of them, right? They kind of clash, and so the solution is in between. Okay, now, if one endpoint is shaded in, does that mean the other endpoint is always shaded in?
Nope, not.
How do we decide? Patience?
Equal to or not?
Yeah, we gotta look at the equal to part. There's two inequality symbols. You gotta look at each of them separately, don't you? So you look at the inequality symbol that is at the end that goes with this solution, you say, should I shade that endpoint in or not? If it has an equal to bar, yes, we will. And then again, same thing here. I look at this one and say, okay, at that end, when with this solution, do I have to shade it? You gotta make that decision separate of each other. It isn't a, if one is, the other one is too. You gotta be careful of that in compound inequalities. So questions about the and ones. Okay, then let's go to the back side where I believe we now move on to example 3, where we're working with the or one. Is there a different way to write the or ones? In other words, can they be brought together and only an x used one time? Did you find anything in this lesson that allowed you to do that? No. Whenever they use the word or, when it is a compound inequality representing an or situation, you have to write them as two simple inequalities. You have to. And you have to solve them that way also.
Two cases.
Yeah. So we have to, but be careful. Just because this one has the same expression that on the left side, and then you notice that Dale and I already noticed that these are opposites of each other, that won't be the case all the time. You have to treat each of them as their own simple inequality and solve each of them on their own, separate of the other. Okay? So what are we going to do? In this case, we get to do the same thing in both of them. What is that? Subtract 2. So we're going to subtract 2 from both sides. I need to get those lines out there so it doesn't look like I'm dividing. Okay? What's the first one's solution? X is less than
-8.
-8. Do we put the word O and? Or. It's, even though it looks like there's going to be two solutions, that doesn't mean we use the word and. So what's the other one? X is greater than 4. So what do you think this would look like wrapped in an outline then? Okay, so -8, would that be first?
Yeah.
Okay. And then 4? Okay.
And then don't shade.
First one says, should we put open or closed circle? Open. What numbers can X be?
Anything less than 8, so it would be going to left.
It'd be going this way, wouldn't it? All the numbers less than -8, so that's going this way. And then the other one says, open or closed circle at 4. Is 4 included? No. What numbers are?
All the numbers.
Any number greater than
Anything greater than 4. So is this a no solution?
Yes.
No,
No.
It has.
because it has solutions. They're just either less than 8 or greater than 4.
The key word is or, isn't it? They can come from the region, X can be from the region that all those numbers that are less than -8, or it can come from the other region. So it doesn't matter. We have both of them on there and we say they're both legitimate because X can come from either region. Okay, so this is our graph for us. Okay, notice the next one that we have to solve. 4x plus 3 is less than 3, or x plus 4 is greater than 9. Is this one of those situations where the algebraic expressions on the left side don't match? Yeah. So, and
This
3 and
one
9
is-
are opposites of each other?
No solution.
You think this is going to be no solution then?
Yeah, because if you solve the first one, it comes out to 4x is greater than 0.
4x is greater than 0?
Less than 0. Divide.
So that means no solution?
No.
Finish.
Okay, go ahead. Divide by 4, is that what I heard next? Okay.
0.
So what's it reading now, Dale?
X is less than 0.
X is less than 0, okay.
And then you do the other one.
Okay. What are we going to do in the other one?
Subtract.
Minus.
Subtract 4, okay. Subtract 4 from both sides. What do we get?
X is greater than 5.
X is greater than 5. Okay. So no solution?
No, there's lots of solutions.
Okay. So 0, 5. Be really careful about this. Just the first one that you solve doesn't necessarily always mean it's the first one on the number line, right? So you're going to be careful about that. And then open circle or closed circle at 0? Open. So x can't be 0, but it can be what?
Less than
It's going to be less than. So all the negative numbers? Yeah. Okay. Can x be 5?
No.
No. There's no equal to bar here. But what numbers can it be?
any number greater than 5.
Any number greater than 5. Okay. This is an or. So I got to bring down my other part of my solution here so I don't forget that I need the word or in between. So x is less than 0 or x is greater than 5. That's all we have to worry about, don't we? So is there a solution? Yeah. We got lots of numbers that can be a solution to this compound inequality. So questions about it? So far, what do you think we can kind of, it's kind of looking like we might be able to kind of conjecture, guess about. What's true? When it's an and, what typically happens on the graph? Or was it shaded? They were connected. It was like shaded in between two endpoints, wasn't it? What happens when it's an or? It was outside from the endpoints, it appears, right? So for a while anyway, let's make the conclusion then that if we have to decide what compound inequality is being represented, we can go with that thought that, oh, if it's in between 2 points, that means there was some intersection, there was some overlap. So let's write the compound inequality that this graph shows. I'm going to give you a little hint. We don't have to worry about there being an x plus 4 or an x plus 9 or a 2x minus 1 or anything. We just have this right here represents x, that shaded region.
Can we just do like -5?
Oh.
So -5
Is
Is less than x, and then -3 is greater than x.
And x is less than -3.
So can I do it like that? Are you thinking?
Yeah.
Because this really says that x is greater than -5. Oh, is it shaded in, by the way, the endpoint?
Yeah.
Yeah,
Oh, so what should we include?
We say greater than.
The equal to bar? Okay, so this one says x has to be greater than -5 and
X has to be less than or equal to.
s has to be less than or equal to -3. So if we, does this mean the same thing as this? We got to decide that. Oh, you need equal to bar here. Does that mean, does this up here mean the same thing as this down here?
Yeah, I'll put the sign on the.
Because this says x is greater than, if we read this from the middle out, does that say x is greater than -5?
Yeah.
And x is less than, read it from the middle out, x is less than -3? So here's our compound inequality that represents that graph. How about this one? What's this one?
X is less than x is less than or equal to -3. Or x is greater than 3.
Or, yeah, this is an or one because there's a shaded region over here and there's a shaded region over here, so it means it can come from either of them, doesn't it? So x is, does this one have a shaded or unshaded dot?
Unshaded.
Unshaded, so then what will we put?
Greater than
Is greater than
3.
3. No equal to bar on that one, right? Remember, they don't both have to have it. They don't have to match, do they? Okay, so x is less than or equal to -3. That's one of the possibilities. Or x is greater than 3. Here's our compound inequality. Okay?